Welcome, this is lecture number 45. In this lecture, we are going to talk about sliding mode control in switch mode power converter. So, first in this lecture, we are going to talk about, we want to recapitulate our geometric interpretation of phase plane of second order system. Then we want to discuss variable structure system and sliding mode control. Then we also want to briefly discuss about sliding surface, switching law, then reaching law as well as the sliding condition. And then system description in sliding motion, like what will be the dynamics under sliding motion, and then what is the meaning of, what is the concept of equivalent control law, and finally the property of the system during sliding motion. So, although sliding mode control will require more number of lectures, but we want to just summarize the overview so that we can understand the basic concept of sliding mode control, but it require more number of lectures hours to go in detail. So, we want to just give the basic idea on the overview of sliding mode control and the primary concept which are needed to apply sliding mode control in switch mode power converter. So, let us first recall our vector field concept. So, in lecture number 42 and 43, we have discussed in detail. In fact, in lecture number 43, we have talked about how to draw vector field when we consider a purely imaginary system, because that means we have drawn the eigenvectors, we have understood, we have using phase plane geometry, using vector field, we have drawn the vector field of real and distinct eigenvalues, for that means the real and distinct eigenvectors, and we have also considered complex conjugate case when the eigenvalues and eigenvector will be complex conjugate. But in that case, we have seen there is something called rotation matrix, right, and that will lead to a rotating motion, either it is with the same amplitude when there is real part is 0, or the amplitude will either keep on decreasing if the real part is negative, and if the real part is positive, then the amplitude will keep on increasing, and that we call as a stable focus or unstable focus and so on. So, here again we are recapitulate this concept, and you can see in this matrix we have considered a regular form where it is generally what we write is that generally we take this complex conjugate case to be R omega minus omega r, and this is a regular form, right. We have considered the A matrix in the regular form, and in this case it is the regular form where r equal to 0 and omega equal to 10, and if this quantity is positive and this is negative, then we know that we have seen we will get to what is called the clockwise motion. That also we have discussed in lecture number 43. Now, we are also considering another system, because in lecture 42 and 43, that one case it is in regular form and the other case we have converted into a coupled form, right. And in the coupled form, we saw the vector field shape were different. In fact, if you recall that let us consider this case where the case 1 we have considered, if we take this first case, we know the vector field will look something like this. As I said that as if you take so let us first draw this axis x1 x2 axis. This is our x1, this is x2, and what we have discussed that for such scenario we will get a circle like this, right. This is a circle, and if you start with this, the motion will be clockwise motion. That is the case here. Now, in case 2, if we multiply with this matrix M, it is a couple matrix, because in this it will look like we have discussed like a basis vectors are along x1 x2. Now, the case 2 we have also discussed, this image will look like something different, this image will look like as if one axis will be like this is my z1 axis, and the other axis will look like this, like a z2 axis, and the shape may look like something elliptical shape, right? And that we are going to see that how does the shape look like when we multiply this kind of matrix, okay? So, we have to recapitulate this vector field. Now, this is a vector field where we have considered r equal to 0 and omega equal to 10, and this is in the regular form, and where this axis is our x1 axis and this axis is our x2 axis, right? And now, if we take an initial vector which is x0, then we have discussed this vector will keep on rotating in the clockwise direction, and since the radius is 0, it will be a circle and which will take this path, right, that we have discussed. And that is exactly is happening. And you see you have drawn the vector field. So, the vector field is actually showing the direction, it is the clockwise motion, and this is the case when we have an x1 x2 where we took the basis vector x1 and x2, and it will initial condition will map like this, and this vector as it will move like this, is a motion, right, with the same radius it will rotate like this, right, it will rotate like this. Now, imagine what will happen for the second case. Second case we have multiplied, and that will change the as if the angle of the image, right. So, initially our vision angle is same, but initially the image as if we are looking vertically down, the image appears to be a circle. Now, we kept our eye position same, but we have inclined the plane, right. So, incline the plane in such a way, we want to see how does it look like. This is like a plane is inclined, right. The same thing again it will be a periodic motion, that means it will again rotate because this is the direction of vector field, you can see the vector field. So, it will go like this, but it is not perfectly a circle because as if the image angle, the plane of the image that got changed, and as a result it appeared like an inclined plane. And this is exactly what we have discussed, that if you multiply with m, the earlier basis vector which were x1 x2, now it got changed to another basis vector vx and vy, and that is why this initial condition we have discussed that can be mapped by spanning vx along this axis and vy along this axis, so that the resultant will look like this. So, the resultant vector will look, this is my resultant vector, right. Now, you can imagine since this is now the new one vector is there, another vector is there as if, so this looks like a plane, and these planes look like an incline, and this is exactly showing that this looks like a plane where the plane angle actually, the normal to this plane actually got changed. Earlier the normal to the plane was actually towards our eye angle, so they are actually matching, but now there is an inclination. So, this is something similar that you can resemble. So, how to draw vector field, and we can actually see how the vector field look like. Why I am saying? Because in case of DC-DC converter, we will see in most of the cases the vector field is complex conjugate, the matrix will show complex conjugate, but this may not be, the matrix will not look like the regular form, because that can be a kind of inclined form, and that we want to visualize, that we have to learn. So, that means this angle plane is inclined as if this is the plane normal. Earlier our normal was this was our normal was like this, like if this is x1 x2 axis, our normal was like vertically up, but now there is an inclination that got changed, okay. So, that got changed. Now, we want to go, that means we talked about eigenvalue and eigenvector of a open loop system. Now, we are closing the loop. Earlier we talked about autonomous system, in 40, 42 and 43, the whole lecture we talked about autonomous system. That means we have only considered this part where we have, and this is we also learned that we derived this model from a small signal model of a boost converter, where we have ignored the perturbation in the duty ratio or the control input, But suppose if the control input perturbation is considered and that control input is a function of states, as if we are trying to design closed loop control. So, in that case we have to incorporate this whole x dot equal to x b into this function. So, this one, and then what we will get is that this whole thing will be our closed loop system, where u is nothing but our minus k into x, because it is a negative feedback system and the gains vector is positive. So, in this case x in general can be n cross 1, that is n number of states, then a must be n cross n, and if the u, that means the duty ratio in our case, is a single input. So, this is n cross 1. So, in our case it is 2 cross 1 because it is a second order system. And the gain matrix K, it is basically a row vector which consists of K1, K2. That means I can think of K to be K1, K2, it is a row vector. Okay. Now, the question is, in order to design this closed loop control, the first thing that we have learned in our linear system theory, the system must be controllable. So, we are assuming that these concepts are known, and this is already covered that in other lecture. So, the controllable system, that means we can design a state feedback control, and if we design a state feedback control, then the closed loop dynamics will look like this, something like this. That means this is our closed loop dynamics, where closed loop matrix will be A minus Bk. That means A is your open loop A matrix, system matrix, B is the input matrix, and K is the gain vector. Okay. Now, once we have considered, that means K to be a set of K1 and K2, now we need to choose the gain in such a way we need to place the closed loop poles in our desired location, right. So, here I am just showing one example. Suppose I choose a K and K which are like K1 equal to 10 and K2 equal to 10, just a simple number I have chosen. You can choose other, because this gain will come from a desired closed loop location, but my intention is to show that even if you choose the desired location and then subsequently you obtain this gain vector, then you can get another closed loop matrix. So, you will get a different closed loop matrix, and for each closed loop matrix we can always draw the vector field, because the closed loop matrix when you write, then it becomes x dot equal to a closed loop into x. So, it looks like another autonomous system in which the control input is a function of state. The whole thing is combined, now it becomes a closed loop system. So, as if there is no external input. Now, the question is, the next question will be how to, that means in the closed loop system design, what we do? We generally consider the closed loop eigenvalue, right, the closed loop eigenvalue. And again, if we write the closed loop eigenvector, this is nothing but our A closed loop into V closed loop, and these are my eigenvector of the closed loop system, right. So, now what we did, we essentially place this closed loop eigenvalue, or in other words, we place the closed loop in a state feedback control. We are trying to place the closed loop poles, or sometimes we interchangeably use the poles and eigenvalues, but unless you consider an output, then there is no concept of pole 0. But in this case, in state feedback control, we generally talk in terms of eigenvalues. In the closed loop eigenvalue, we can choose based on where we want to place the eigenvalue, because it will indicate our closed loop performance. That means what will be my transient, overshoot, undershoot, etc. There can be, the specification can come from time domain specification and so on. But we can place the closed loop pole, and accordingly we can design this gain matrix. But what will not be in our hand is that how to place the closed loop eigenvectors. That means it is a problem of eigenvector assignment, because even though we choose a closed loop eigenvalue, our closed loop eigenvector is not in our hand, because if there are 2 cross 1 matrix second order system, so we will have 2 eigenvalue to be placed, and in order to place that we will have 2 variable, that is K1, K2 gain. So, that means for getting this eigenvalue I need to choose this gain. So, I have no freedom, degree of freedom to place the eigenvector. So, it is the only eigenvalue placement. So, if we do not take the eigenvector or we cannot place the eigenvector, the problem will be the shape of the trajectory, because we have discussed that two subsystem where the eigenvalues are same, but they have completely different eigenvectors. That means, if we make a linear transformation of the system, we transform this closed loop system to another plane by multiplying. It is like an image, because as if this trajectory motion, if we change our view angle, you will see our nature is different, right. But the stability property is decided by the eigenvalue. So, those are fixed, that means that is not going to get affected, but the trajectory motion, the nature of trajectory or shape of the trajectory will be different. So, this is where actually is the problem in the one of the aspect in linear control system, because we have almost no choice to decide the shape of the trajectory by means of linear control, because we can only place the eigenvalues. So, if we want to shape the trajectory, that means I talked to you the closed loop eigenvalue and closed loop eigenvector. So, when we talk, we place these eigenvalues, then we can find out the A matrix, and from the A matrix and the eigenvalue we can find out the eigenvector. Suppose I want to get my trajectory something like this. Suppose imagine that I want to shape a line, straight line. Suppose this I can call something similar, because what we discuss, if we have discussed that what is the property of the eigenvector. So, we know that eigenvector has something called invariant property. It has invariant vector field. What is that? That means, if I can define, suppose for this system we got two eigenvectors, one eigenvector, let us say along this line, let us say this is my one eigenvector, and the other eigenvector, for imagine it could be like a Vy, the other eigenvector is Vy. Okay. Now, if you choose an initial condition, suppose we choose an initial condition here x0. Now, how does this trajectory move towards this origin will be decided by two eigenvectors, right, because we have learned that x of t can be written as e to the power lambda 1 t alpha 1 Vx plus e to the power lambda 2 t alpha 2 Vy. So, we have control over lambda 1 lambda 2 because that we are placing, but we have hardly any control over this, that is one fact. The second thing, we know the eigenvector, if we only choose let us say a point on this eigenvector, if it is a stable eigenvector, then the trajectory will move along this line, right, it will not go out of the line, because that we have learned from the something called invariant property. Similarly, if we choose an eigen in an initial condition here, the trajectory will move along this eigenvector. So, we can only ensure the movement of the trajectory along one of the eigenvector if we choose the initial condition on it. But is it possible that if we choose suppose in this system I want to create a path, suppose I want to create a path, let us say this is my let us say this is my point, I want to create a path. Okay, let me draw properly. I want to create a path. Okay, this is my path, and I want to make sure if I take any trajectory here, I will do something so that it will try to come towards this, and once it touches here, it should remain here, it should remain here. Or if I take an initial condition here, it may come towards this, but once it moves, it should remain here, it should go along this line. That means it is something like, because what does the eigenvector says? That means if you take your initial state along any of these eigenvector Vx or Vy, the movement of the trajectory will be constrained on the eigenvector. That means if you have a two-dimensional plane okay, and if we have two distinct eigenvectors and of course they are real, then each eigenvector each will look like a line, look like a line, or in other word one dimensional plane, because each eigenvector will, remember, it will define, like say if we extend this eigenvector, that means if we keep on extending, any point you choose here, it will move along this line. So that means if you choose any initial condition of this vector, it will always remain on this line. So the motion of this particular point, or basically the initial condition or the trajectory, will be constrained on the line, even though you have a two dimensional plane, but the motion will be only along that line. So you can think of this dimension of this line is just a one dimension. Similarly, for the other eigenvector, it will be another one dimension, but we want to get for any arbitrary initial condition, is it possible that by some means we want to force this, and this will look like my another z, which is synthesized eigenvector, looks like an eigenvector which can be maybe a linear combination of eigenvector, or it is our own design, where in the entire two dimensional plane the trajectory will always is forced to come towards the line, and it will remain on the line, and then whether it will come towards origin or go away from origin, that we will discuss later. But let us say, is it possible to have a scenario where we want to force and it will remain on the line? So that is one of the objectives, and that probably is not possible in case of linear control system, because in linear control system, for a second order system, if we get two distinct eigenvector, then each of the eigenvector will be invariant field, but for any arbitrary initial condition we cannot make a one dimensional motion, right. So that is one of the problem that we are looking for, because why we are interested, why we are interested in finding such movement, because this path we want to shape. Suppose we want to get a desired trajectory which will try to satisfy certain optimization criteria. Suppose I want to achieve something like minimum recovery time, or we want to reduce that, we want to minimize some energy, something like that, or we want to constrain the motion such that the fuel economy can be improved, the disturbance rejection property can be improved. So many things we want to discuss. So now, and you will soon find that this might be possible if you incorporate the switching control. So simply by linear control it is not possible. But interestingly, a DC-DC converter is a switching converter. So you do not need to do switching like in linear system. If you apply a switching control, that means it is a discontinuous control. But in DC-DC converter, your control itself is discontinuous, because we have a switch, and that switch will turn on and off, and you will get two different subsystem, and each subsystem we want to drive in a way so that our resultant motion can be along the desired trajectory that we are talking about, that means along the green line, right. That is one of the objective. Now in the switching system, this DC-DC converter, we have discussed that we can obtain the state space switching model, and we discussed that in general it is written as x dot equal to AQX plus BQV in, where AQ it is a function of state, the switching function. But in case of buck converter, your matrix, input matrix, if you, for the ideal case, this AQ will be A, it is independent of Q, as long as this is in continuous conduction mode. But this structure will be different when you go for continuous and discontinuous combination. Similarly, if you go for a real buck converter with parasitic, with diode drop and all, this A matrix can be different, and that also dependent on the switching matrix. But if you take a synchronous buck converter with almost identical RDS on and RL, so in RDS on, then you will find that this A matrix will be more or less same. But the B matrix is different, because in the buck converter, if the switch is on, the input is connected, right, but the switch is off, then input is disconnected. So, the input matrix is totally discontinuous. So, you will get a discontinuous vector field. Now, if you just take only on state trajectory, that means here I am talking about for this model, if you take q equal to 1, then you can get this vector will comes in, input is connected, and for q equal to 1, that means your q, you can substitute q equal to 1 here. What will get? You see, the trajectory or the vector field will be decided by this matrix, whereas this quantity will decide your equilibrium point, that means what is your operating point. If this quantity is not there, then your origin is the equilibrium point, because we talked about x dot equal to ax plus bu. So, here you can think that u can take, either it can take u plus or u minus, two discontinuous input. So, if depending on this u term, discontinuous term will only shift this operating point, right, but the vector field, the nature of the vector field will be decided by this A matrix. So, in this case, it is very clear that if we take the initial condition, that means this is our initial condition, and you can see it is going in the clockwise direction. So, it resembles something our concept that our regular form, what is our regular form for, that means it is definitely a complex conjugate case where the motion is like a circular or maybe oscillatory motion, and either the the amplitude of oscillation is decreasing when the real part is negative, but it may not be in the regular form, because we saw in regular form it will look like a pure circle, and in case of image version of that where it is not in regular form, but still the eigenvalues are complex conjugate, then you will get an inclined either elliptical shape or something like that. So, here it will be elliptical shape, but since the motion is decreasing, slowly decreasing, so it is called stable focus. Since it is not in regular form, it is not in regular form, because it is not in terms of this r, whatever learned, it is not. What is the regular form? So, the regular form is something like r omega minus omega r, it is not in this form, but it is a complex conjugate case, and but the real part is very small, so it is decreasing very slowly, and you can see the vector field, it is showing in this direction, it is showing in this direction. So, it is a clockwise motion. And what is my operating point? Because it is switch on and I took input voltage to be 12 volt, and what I chose R I have taken R equal to 10 ohm. So, if you turn on fully on the switch, the final steady state voltage will be equal to the input voltage, and that is exactly is the 12 volt here. Here in the output voltage it is 12 volt, and what will be here, because it is current will be what? In final current will be final voltage by resistance. If the final voltage is 12 volt, is 12 by 10, so it is with 120 milliampere, right? That means 12 by 10, that is 1.2 ampere, 1.2 ampere, okay. So, now 1 point, so it will be somewhere here. If you take the off state trajectory, the same, it will be again complex conjugate, and you can see it is rotating in the clockwise direction. That means it retain the fundamental nature of the clockwise motion, but slowly decreasing, but the operating point get changed here. Since this will be 0, q will be 0, so this part will not be there, and in that case your origin is the equilibrium point, and this is 0 0, you can see this is 0 0 point, right. But the DC-DC converter, we never operate either fully on or fully off, because we operate in on off state. Now, if we increase the load current or decrease the load resistance, what will happen? You see the current has drastically increased, because now we are using R equal to 0.1, and what is my final voltage? So, if the switch is on, my final voltage will be simply V in, that is 12 volt, and my final current will be V in by 0.1, which is nothing but 12 by 0.1, so it is 120 ampere. So, it is roughly 120 ampere, 12 volt 120 ampere. But what has changed, you see, again it is a clockwise motion, but the damping ratio has increased, the real part has increased. So, compared to the previous eigenvalues and this eigenvalue, the real part, it is negative only, but the magnitude has increased, so that it is decaying much faster. For the same time scale, you see the oscillator is quickly decaying and coming back, because we will see in DC-DC converter, we have seen even in the subsequent lecture, under light load condition or high load resistance, there is a damping problem, poorly damped, because the complex conjugate is a very low real part, small real part, but here the real part is large, so it will quickly decay and will very quickly come to steady state. Similarly, if you take fully off, the nature of the clockwise motion will remain same, it will again decay fast, but this point gets shifted to 0, 0. So, that we have discussed, but we never want any of on, like a fully on, fully off, and light load condition we really face difficulty in terms of controlling and to get the desired response. Now, again coming back to the question, how to obtain, I want to make sure my whole trajectory will look like an eigenvector. That means, if you see here, this line indicate our on state trajectory, that means this color, particular color are the on state trajectory, and if you see the green one, these are the off state trajectory. But now we have placed something like a line, you see this is a line, straight line, this I can say this is a straight line, kind of a or a 1D plane, or basically a straight line, right. It is basically a line. This line, where it will terminate, it will slowly come and it will terminate 1, because here again is my output voltage axis and I want the 1 volt to be my desired output voltage. So, my reference voltage I want to be 1 volt, and what I said, load resistance in this case it is 10 ohm. So, the current will be accordingly, at 1 volt, that means my load current will be, what will be my load current? My load current will be V0 by 10 R, so it will be 1 by 10 ampere, so it is something like 100 milliampere, that I want 100 milliampere. So, this is my final point. Now, how can I achieve this motion? That means, you see the on state, the trajectory is moving, this is the movement of the trajectory. When it hit this line, so there is a red line, you can see red line, and we will soon see, then it remains there. That means, whatever initial condition here, we have taken an initial condition which is 0, 0, that means the converter is starting from the 0, 0, 0 current, 0 volt. Then it hit, it turn on, when it hit, then it is moving along the line. How are you going to move? That we are going to discuss. So, we are placing something called a surface. So, this red one, what we are indicating here is basically, you can say there is a surface, a red color, which is like this, because a straight line, here it is the voltage and it is the current axis. So, some gain into current, and a reference current is the desired current where you want. So, what is that? It is something like a Vref by R, that is my reference current, and what is my reference voltage? That 1 volt where we have set. And whenever the surface equation is sigma, which is this equal to 0, that means if the trajectory is there, this will be simplified to 0 and it represents a one dimensional motion. And if we further normalize, you divide by Kc, it will look like a gain, it is like a current error into proportional gain, is like a we are talking about a proportional control, is like a proportional control and sigma, and this you can get more detail about this geometric control in the element of power electronics. So, that means now we need to make some switching arrangement, which tells us we need a switching surface. So, this is what exactly I was telling about. This is my sigma, and here the sigma I have taken IL minus Iref into Kp V0 minus Vref. And what is the slope of this line? It turn out to be minus Kp. That means if you increase the proportional gain, the slope will also increase. And we want to see, that means we want to get this line in such a way it meet our desired requirement. Okay. So, here we have chosen some value of Kp and it turns out to be like this. But remember, when it hit the surface, it has to turn on and off, and in such a way this side as if it is going towards the line, and this side will turn off as if it is coming towards the line. So, the vector field in either side should be towards this line, so that it will finally converge to this line, and then you have to see whether by virtue trajectory at all is moving towards the desired point. This is the desired point or not. So, this is the desired point where the load here is, here we have chosen R equal to 0.1. That means our output voltage should reach 1 volt and output current should reach 1 volt by R. So, which is nothing but 10 ampere, and that is somewhat it is coming. Now, what happens if we increase the slope of the line, that means we increase this gain. Okay, this is the time domain behavior. This is the the trajectory or basically phase plane output voltage versus inductor current. Now, I am showing individually how does the inductor current look like. So, initially it will turn on, from here the switching operation start, but it does not look like there is switching because we have taken a very narrow band, because you cannot keep a pure surface because your switching will be infinitely fast and that is not desirable. So, we want to take into account all these practical constants. So, now this is the scenario where, as I told, that this is my Kp slope. That means, if I increase Kp, the falling slope and the slope will increase. So, gradually this line will, it has to pass to this point. So, the line may look like this. As you increase the Kp, this line will look like this. Okay. Now, with a higher line, you see first the trajectory hit here, then it turn off, but it may not, because this movement it is decided by the off state trajectory. So, this is the off state trajectory, because we have already drawn the vector field, and this is my on state trajectory. And this line is the sigma, or we can say this is a switching surface. So, since it is a fast one dimension, it is a straight line. So, in this case the surface dimension is just a one dimension, but here your sigma equal to 0. And here you can see the switch turns on, it hit, switch turns off, and then it comes to steady state here. And if you take the time domain behavior, the switch turns on here, then it completely turn off and it come here, and there will be small switching here. Okay, very lower switching. Okay, so that means practically there is a band, but which is sort of not clearly visible because the band is so narrow. So, on top of rate, that means we have considered the actual sigma, which is 0. There has to be some band, that means it should have one band here and it should have another band here, and the trajectory will actually go, it will remain on this line, that means it should move like this, something like this. So, if we go, okay, now these two band, one is as I have drawn, I can draw again. This is my line, this is my sigma equal to 0. The one line I have drawn is just above this, and the other line I have drawn is just below this. So, this is my sigma 1, this is my sigma 2. So, sigma 1 it is just on top of this and sigma 2 just below this. Okay. And if you take a larger gap or basically band, if we increase, then you see this on off operation and you can reduce the switching frequency. That means you can increase the ripple and the switching frequency can be reduced. So, by adjusting this band, we can effectively control the switching frequency, and that is one of the problem, but it can be addressed. So, that means this results into something like a variable frequency operation, but you see if you do it properly switching, it turn off. This is my on state trajectory, as I said, my on state trajectory. This is my on state trajectory, and this is my off state trajectory, off state trajectory, and this will come here. Here your switching takes place. So, here your actual switching takes place, takes place. Now, it is slowly comes towards this origin, and if you see the we'll discuss about this, that how to design this sigma and all this we will discuss. Similarly, if you consider a boost converter, where this green line, if you see this green, these are the on state trajectory, and in boost converter when switch is completely on, you see the current is increasing, that means it is in the upward direction, the current is increasing, and in this side voltage is going towards this. So, that means it effectively shows the current is increasing and the voltage is decreasing. So, as a result, your resultant vector will be something like this. This is your resultant vector, and that is exactly what you are getting. So, voltage will start decreasing, and if you continue turning on the switch in a boost converter, you will find the voltage will completely collapse and the inductor will saturate because the current will increase significantly and it can damage the converter. So, you have to be very careful about the switching mechanism of a boost converter. During off time, when this RLC circuit will be connected, then it is similar to a buck converter where we have a complex conjugate pole, and there you will have a that kind of a spiral motion that we have discussed. That means the trajectory will be like this kind of motion, slowly decreasing motion for off state. Okay. So, if you draw the complete trajectory, now the question is how to turn on. So, this is my on state trajectory, because you see this blue line is parallel to this green line, right? The green line where your actually, if you look at this green line, and they are almost parallel. So, this indicates the on state trajectory. And if you see the off state trajectory, that means if you see this off state trajectory, this is parallel to this trajectory, right? This trajectory, magenta color, which is the off state trajectory. So, that means when the converter hit this red curve or the switching surface sigma, then it turns off, and it turns off, it follow the trajectory off state, again it comes, and this time now in both sides, because you see the green line, it is towards this side, and if you see this side, it is towards this side. So, the magenta line towards this and the green line towards this. So, as a result, the trajectory will move along this path, because in either side the trajectories are towards the surface. But if you see here, the trajectory is going out, the off state and going away, and the on state is coming in. So, this is something called refractive trajectory, where one side the trajectory is coming towards the surface and the other side is going away. And this is the reflective or where the sliding motion exists, and we will discuss this, where the trajectory actually moves away, and we will discuss about reflective, refractive as well as the rejective trajectory in the subsequent lecture. Yeah, so here also we will have a surface we have discussed, that is also again the same thing that we discussed for a buck converter. So, the trajectory shaping within switching control, that is the best way, because that we discussed. If we want to get a motion where sigma equal to 0. So, that means for a two-dimensional plane, because it consists of x1 and x2, I want the initial condition will slowly come, hit this red line and will remain on the line, and in two-dimensional plane we will see this switching surface sigma equal to 0, that indicate just a straight line. So, we want to confine the motion along the straight line, and it is something similar to our eigenvector, it becomes like an invariant vector field. That means once the state reaches here, trajectory reaches here, it will remain on the line. So, as if it will satisfy the invariant principle, and then if we make sure, because the invariance principle is the eigenvector property, but whether it is a stable or unstable, that depends on the stability property that will come. But here we need to make sure the invariance property. So, if you can force the trajectory to move and touch this line, and then it will remain on the line. So, it is something similar to the concept of eigenvector, but that is not possible in a linear control system. That means we cannot have a desired eigenvector, only one in the whole two-dimensional plane, where the trajectory will come and remain on the line. So, that is required something like a switching control, and that is exactly what, and it, you see, when the switch is on, that means you take U, which takes a discontinuous control input. So, this input in case of our linear feedback system, we took k equal to minus kx. So, that means a linear function of state and the gain, but here, so this is in case of linear control, linear state feedback control, right. But it is a switching control where the control input takes either some plus or minus, as if you can differentiate. Suppose if you are using an op amp, so op amp is used like a, in first case linear control, op amp is using like a linear amplifier, and in case of switching control, op amp is acting like a comparator. So, on off, it just take between plus and minus. Okay. So, that is how we can differentiate. But in U plus, that means for positive supply rail and the negative supply rail of the op amp, you will get two different vector field, because if the A matrix even common, we saw earlier that the trajectory in case of buck converter, you see, we have seen that it was a stable focus and it was rotating in a clockwise direction and slowly coming, but the change in U will only shift the equilibrium point. That means we saw for on state and off state of a buck converter, the nature of trajectory was same, but only the operating points are different. So, here also the operating point will be different. So, that is why it is a variable structure system, because these two operating point create like a two structure, and we need to make sure that will come that if you take U plus, that means if you take U plus, your operating point where it will eventually try to move should remain in this side, because it should try to come towards this operating point, and when it hit the surface, then it will get locked. Because if you take U minus here, your xe minus should be this side. So, by that we can make sure the trajectory will neither go towards xe plus 1 completely, or it will not go towards xe minus 1. So, it will finally get locked into the switching surface and will just make a switching operation, on off operation. So, that constitute a something called variable structure system, where we have two different vector field, discontinuous vector field, and the point of discontinuity will be just either side of the switching surface. So, on off control and is a discontinuous vector field. So, this start with our buck converter that we did, where this something create our discontinuous vector field, where it can take either 1 or 0, and that shift the operating point, but at the same time the vector field gets shifted here, right. That means at the same in the phase plane, at one particular point the direction of vector field will be different for two different switch states. So, it takes a discontinuous control input, and we have seen that this our is sigma, right, and they will move along this path. So, it looks like we are trying to shape the eigenvector for this practical system, or basically a trajectory we are trying to shape along this direction. So, these are the basics of sliding mode control. That means you take either a linear control that we have discussed, or even you take a nonlinear control where along with the linear part, if you separate out, there will be some nonlinear term. That means it is now we are talking about a generic term where this state space has n dimension, n number of states, and definitely this will be n cross n. But here we are talking about a generic where we have m number of input. We talk about only single input, but you can have more number of input. In fact, sometimes we introduce more input, like over actuated system, under actuated system, like that. So, in over actuated system we put more actuator or more control input because we want to achieve certain desired behavior. For example, if you go to robotics, the robotic arm, there can be sometimes people use under actuated system. That means there can be only one motor to control the entire movement of the hand, like we have knee, shoulder, but suppose you only put one motor at the shoulder, but there is no motor in the knee. So, then it will be difficult to get it, but maybe it is possible. But suppose if you put another DC motor at the knee as well as shoulder, then you can effectively control the movement of the hand. Okay. But we can also place few more actuator in order to even precisely control in different direction with certain objective of optimization problem or trajectory shaping problem. So, we can sometimes have more number of input in order to meet certain optimization criteria. But sometimes penalty is that more actuator we have to pay more, right. So, that also we need to discuss, we need to take into account. But here if is a vector field, and where we have already discussed this linear part for DC-DC converter where A matrix was linear. In case of boost converter, A is also a discontinuous matrix because it will be a function of Q. But B was in buck converter is a discontinuous one, right. So, the U that means either U plus or U minus. But in more generic term, you can also have nonlinearity in the state space model, okay, and this nonlinearity can be inherently that system is nonlinear, or sometimes we miss out some nonlinearity due to the model uncertainty, so all these things can be incorporated and still this concept is applicable. So, here we are assuming the number of inputs are less than number of states. So, that means m is less than n, but m can be 1 or more. Now, we are talking about a sliding surface because we already discussed sigma x, and where sigma x equal to 0, that we have discussed. But we want to see what is the dimension of the sigma, and that will be decided by this s, and that will come because sigma is equal to s into x. So, if x is n cross 1, okay, and how s is coming? S comes is the number of input. So, if it is a single input system, then this s will be, it is basically s is m cross n. So, if the one input, then s will be 1 cross n. So, this sigma will be simply a straight line because it is a one dimensional plane where that means we are talking about sorry, it is not a straight line, I will say it is a plane. If let us say we are talking about a third order system, where n equal to 3 and one input, control input, that means u dimension is 1 cross 1, then s should be what? S should be 1 cross 3 and sigma is 1, so equal to 0. That means you will get sigma x something like k1 x1 plus k2 x2 plus x3 equal to 0. And if you write this in the 3-dimensional plane, this can be written as as if x3 equal to minus k1 x1 minus k2 x2, as if x1 x2 like a two dimension, like x1 axis x2 axis, and we can get the x3 by combination of x1 x2. So we can see that this will resemble like a two dimensional plane. For a three dimensional system, this will represent like a two dimensional plane because it is a combination of two independent, let us say x1 x2 is the axis where the basis vector, eigenvector is along x1 axis and along x2 axis that we have discussed. So x3 component is a weighted combination of two eigenvector. So naturally there are two independent eigenvector and the third vector is derived from the two vector. So it is a dependent one. So as a result it will be a two dimensional plane. So that means we'll talk about this hyperplane concept, and but we need to make sure this switching surface should be equal to 0 because we want to constrain this motion on this surface, it should be equal to 0. So now if we talk about the sliding surface, as I said S is a hyperplane. That means if we take m equal to 1 and n equal to 3, then we have discussed this S dimension is 1 cross 3, which means that if you go into the three dimensional place and the motion is constant along this particular sigma x equal to 0, and it will look like a two dimensional plane because what is our sigma x that we have again discussed? It is k1 x1 plus k2 x2 plus x3 equal to 0. So this will something similar to x3 equal to minus k1 x1 minus k2 x2. Since x1 is a dimension, you can think of a basis vector, x2 is another dimension, think of another basis vector. So the third vector is derived by combination of two basis vector. So that means it will be on the x1 x2 plane, it cannot have any z component because the z component x3 is derived from these two, right. So that means for a second order system, sigma x like this. So this will be a straight line. For a second order system, S will be 1 cross 2 and sigma x will be k1 x1 plus x2 equal to 0. So we will get x2 equal to minus k1 x1, and this is the equation of a straight line passing through origin where the negative slope k1. Okay. So this is called hyperplane. The hyperplane gives you the dimension of the switching surface. How does it look like? Whether it is a line, whether it is a plane or it is a surface. Now if we talk about one input, I discuss three states, then we will get sigma x equal to k1 x1 plus k2 x2 into x3, and this will look like a plane that we have discussed. That means this plane is a combination of x1 x2 or x3, but its motion is restricted in this plane, and this plane, the dimension of this plane is a 2D plane. It is a 2D plane, whereas the x will be, x is basically belong to three dimensional plane. In a three dimensional plane, we want to restrict the motion to just a plane of two dimensional, that is sigma x equal to 0, right. That is a switching hyperplane. For second order system, the sliding surface is just a line. That means S equal to 1 cross 2. For third order system, for a single input, we have discussed S is 1 cross 3. It is a plane. This is the case. And for fourth order system, S will be 1 cross 4. So it is a 3D surface, three dimensional surface, whereas the system order is fourth order. So interestingly, you will find this hyperplane dimension will be 1 less than the system dimension. That means if the system is second order, the dimension of this hyperplane will be first order, first 1D, 1 dimension less. If the motion, the state vector is third order, then this hyperplane dimension will be second 2 dimension. So 1D less. Now if you consider 2 input, 3 state, 2 sliding surface, so there will be S has 2 cross 3, that means we have sigma 1x, sigma 2x. Sigma 1x is k11 x1 plus k12 x2 plus x3 that equal to 0, and sigma 2x will be k21 x1 plus k22 x2 plus x3 will be equal to 0. So, the two different coefficients, so two planes are different, but each cases the sigma 1 and sigma 2x are the two planes. But the hyperplane which indicate 2 cross 3, that is a combination, and you can see this hyperplane is a intersection line which is a one dimensional. That means each of these switching surface is a second order, two dimensional. So, you can think of this hyperplane dimension when you write S m cross n, you can think of the dimension of this hyperplane is n minus m, that is the dimension. So, for in case of third order and two control input, so n means 3 minus 2, it is a single, and that is nothing but the intersection of the two plane, which is nothing but just a straight line. It is nothing but a straight line passing through origin, and so S hyperplane will be n minus m, it will be a one dimensional, just a line 1D. So, that means we want to restrict the motion along this, so that it will become one dimensional motion even though the system is third order system. So, 3D trajectory, that means we talked about in DC-DC converter the second order current and voltage, we want to confine the trajectory like a first order hyperplane, it is just a one dimensional line. In case of there, if we have another input, if the state vectors are, there are 3 states, then we can confine the motion into one line. But whether it is possible or not, that we are going to discuss, but this is a physical realization of sliding motion along what is the dimension of the motion. So, in this case it is a one dimensional motion along the line. So, the switching law, if you consider switching law u plus and u minus, and for each, because we know that suppose for example x dot equal to f of x comma u. So, f plus it indicate f of x comma u plus, and f minus it indicate f x of u minus. Okay. And we are taking this in the either side of the plane. That means, if we consider our x1, x2, it is the second order system, for example, we consider, and suppose if we draw a line like this, and this is my sigma x that is equal to 0. So, this side if we take u plus, so u plus on, so this is my f plus and this is my f minus, and I told you for f plus the equilibrium point x e plus should be in the other side, so that the trajectory will actually try to cross the line, it should cross the line, it should go towards this, because it is trying to go towards the equilibrium point, but it cannot go because there is switching line which divide the switching law, because here you have switching law u minus, here you have switching law u plus. For this f you will have x e minus in the either side, this side. So, this is a discontinuous vector field, and particularly towards the switching surface either side you have a discontinuous vector field. So, we have discussed about the switching law and basic concept to switching control logic under sliding mode control. So, we will continue sliding mode control lecture in the concept of reaching condition, their understanding of switching law more detail along with a buck converter case study in the next lecture. So, we will continue this in the next lecture.